Hello everyone. In this video I'm going to talk about performance evaluations for classification models. If you recall from the previous videos, we talked about the problem of overfitting. Overfitting occurs when a model corresponds too closely to a set of data but fails to predict future observations reliably. In other words, an overfit model accounts for the noise in a particular set of data rather than the underlying patterns that can be generalized to future observations. In order to overcome the overfitting problem, we partition the data and use cross-validation to detect overfitting. So if you remember, we partition the data into two sets. One is training set and the second one is validation set. In training set, we used to build one or more predictive models. And training data set trains the data mining algorithms to identify the relationships between the predictors and the target variable. Validation data set is not involved in the model building, but you use validation dataset to measure the predictive power of the models that you have identified and built in the training dataset. And we use the root mean square error to choose the best model. The model with the lowest root mean square error was chosen. Some analysts use tree partitioning technique. In tree partitioning technique, you have a training set, you train the model, validation set, you select the model, and finally, you have the test set in which you evaluate how well the final model performs. And this figure explains the overfitting problem. Blue line represents training error rate and orange line represents validation error rate. As you increase the model complexity, first both error rates are decreasing, and after some point you see that the validation error rate starts to increase, although the error rate in the training dataset is decreasing. And performance measures used in classification and prediction models are different. Therefore, I discussed them separately, starting with performance evaluation for classification models. Performance measures for classification models can be computed from a confusion matrix. A confusion matrix is a table that summarizes classification outcomes obtained from the validation dataset. Here you see on the screen one confusion matrix for a binary classification problem. Assume that the target class, also called the success class, is class 1 and non-target class is class 0. From the confusion matrix, we see that two correct classifications are possible. True positives, in which case actual value is class 1 observation and you also predict as class 1. In true negatives, the actual class is 0 and also you predict the variable as class 0. Conversely, two incorrect classifications are possible. False positive is a class 0 observation that is incorrectly classified as a class 1 observation by the model. False negative is a class 1 observation that is incorrectly classified as a class 0 observation by the model. We have 5 performance measures for classification models. The first one is the misclassification rate. You may also call this rate as error rate, proportion of observations that are misclassified. So if you remember, we have false positives and false negatives. So it's the proportion or the ratio of false positive plus false negatives to total cases we have. Accuracy rate is the opposite of misclassification rate. It is the proportion of observations that are classified correctly. True positives plus true negatives divided by total cases. Sensitivity is the proportion of target class cases that are classified correctly. Sensitivity might be confusing, so let me explain to you. Let's say you have a breast cancer test. And in sensitivity, you are focusing on class 1 or patients that have cancer. So here you want to identify among the class 1 patients are actually correctly identified. So you're looking at true positives among cancer patients. If we say that class 1 is the cancer, then you're looking at the number of total cancer patients, which is the sum of TP plus Fn. That is the sensitivity rate. Precision is the proportion of predicted target classes that belong to the target class. Now let me explain to you precision. It is the proportion of predicted target classes that belong to the target class. So instead of dividing the sample into two, cancer and non-cancer, this time you are dividing the sample into positives and negatives. So you're looking at total positives. Total positives are here, TP plus FP, and you're trying to find out the proportion of predicted target classes, that means true positives, in the target class of positive tests. Next, specificity. In specificity, you calculate proportion of non-target class cases that are classified correctly. This time, you are looking at this class, class 0. Instead of class 1, you are targeting non-cancer patients, class 0. So total number of class 0, FP plus Tn. And you're looking at the proportion of non-target class true negatives. For example, a predictive model with 100% specificity would correctly identify all patients without cancer. A model with 75% specificity would correctly identify 75% of the patients as cancer-free, true negatives, but remaining 25% of patients who are cancer-free are classified by the model as having the cancer. Next, let's see one example. Here, class 1 target group is the social media users who purchase at least one product after receiving a promotional message. Class 0 is the group of social media users who do not make a purchase after receiving a message. We want to calculate first the accuracy rate, then sensitivity, and then precision, and then specificity. Predicted class 1, actual is class 1, so this is true positive. Here is true negatives. Here we have false negatives, and we have here false positives. In accuracy rate, the first one, correctly identified TP plus TN divided by all observations. Therefore, numerator is 29 plus 133 and denominator is 29 plus 133 plus 19 plus 19, which is 0.81. Second, we calculate sensitivity rate. In sensitivity rate, we are looking at class 1 who purchased at least one product after receiving a promotional message, which in this case is the sum of TP plus Fn. 29 plus 19, and we are looking at true positives here, 29, which is 0.604. 3 is the precision. For precision, we divide the sample into predicted class 1 and predicted class 2, and we focus on predicted class 1. TP plus FP. Among that people, the true positives, which is 0.604. And 4, we calculate specificity. Here, our focus is class 0. Among the class 0, which is 19 plus 133, how many of them are true negatives? 133. And that is equal to 0.875. This is how we calculate the performance measures of categorical data. The cost of misclassifying a buying customer as a non-buying customer, which is the loss in profit, is often much higher than the cost of misclassifying a non-buying customer as a buying customer. In such cases, marketers tend to pay more attention to sensitivity measure than to the overall accuracy rate. Okay, accuracy rate, as you see, not only focuses on true positives, but also true negatives. So if you have lots of true negatives, that means you correctly identified non-buyers, your accuracy rate may be high, but your target is buyers. And buyers usually are a small part of your sample. So you want to see among your buyers, okay, all these buyers, how many of them you correctly identified. And here, sensitivity measure is much more important than the accuracy measure.